basic points of this theory, it goes back to Einstein's general relativity, which was published by him in 1915, and additionally goes back to the French mathematician Eckardt, who lived about in the same time as Einstein, and finally on Myron Evans, who was born in 1950, is a professor in Wales, Great Britain, and was first a chemist and physical chemist, and finally developed this unified field theory. You know, if you consider the general status of physics in the last 100 years, the 20th century started with Einstein's general relativity as a milestone of new results. When quantum mechanics was developed, a completely different field, had nothing to do with the classical theory which Einstein propagated. And from quantum mechanics we got quantum field theory, it's more complicated, and the basis of the particle theory, particle zoo, which we have today, for example, what they are looking for in CERN, and the big accelerators is all based on theory, on quantum field theory. And Evans made a radically new approach, found it in 2003, and the hope is, or it looks really like that all these big theories can be greatly simplified by this approach, therefore it's so interesting. Yeah, in short, what is behind this theory? You know, Einstein found the curvature of space as the reason for gravitation, described gravitation by geometrical means, by geometry, and used curvature of the so-called Riemann space, developed by the mathematician Riemann in the 19th century. In addition, Cartan introduced a torsion into this Riemann space concept. That means it's also called external curvature. I won't go in too much details here. You can imagine this torsion as a small field or a vortex field. And you know, magnetic fields are vortex fields, and this is the essential idea Evans had to describe electromagnetism by this torsion or curl-like fields which were introduced in geometry by Cartan. That's the essential new point here. And all other consequences go back to this idea. Yeah. ECE theory, short form for Einstein's Cartan-Evans, is based on rock-solid mathematics. There are no hidden assumptions or something like that, or ad hoc assumptions. It's based on three mathematical axioms. The first is that the electromagnetic potential is proportional by a factor to a quantity of geometry. In detail, this is the coordinate transformation, transforming the ordinary free space or four space to a so-called tangent space in Cartan geometry. For the specialists, we will need not go into much detail here. Essential is that this geometric quantity is interpreted as a physical potential, for potential. That means electromagnetically scalar potential plus vector potential, from which we have already heard today in the morning. The second axiom, which follows from the first, indeed, is that the electromagnetic fields are nothing else than the torsion of space-time. That means these Kerr fields, which I showed you in the foregoing slide, are nothing else than the electromagnetic fields also connected with this constant factor. And the third point we have to introduce, which is important for quantum mechanics, that the curvature is proportional to the electromagnetic density, the momentum and energy density, the density tensor, and this goes back to Einstein, who already introduced this ansatz here. So these are the three basic points of the theory. Let's look at it, in what it results. Sorry, the slide has been anyhow come to disorder here. A theory needs equations which you can solve, and when you solve them, you get the results of the quantities you want to know. In this case, the quantities to know, looks very strange here, sorry, are the electromagnetic fields. If this would have been written correctly here, you would recognize Maxwell's equations, essentially, with an extension that divergence of B is not necessarily zero, but could have final values. Also for the Faraday law, that means this ECE theory allows for magnetic monopoles, but that is not clear if they exist in nature. So normally we set these terms to zero. And then you have formally the same as Maxwell's equations, but with a difference, but the fields relate to a space-time which is curved and has torsion. In normal Maxwell theory, you take as an assumption the special relativity theory. That means you have no curvature of space-time. Here, curvature is included. And this difference can be seen only if you look at the definition of the fields from the potentials. Sorry, this equation is totally messed up. There appear, let me say it in words, besides the vector potential and scalar potential, there appear terms called omega, which represent curvature and portion of space. And these terms